Now what we are going to do, again I do not need it, but I will just start with this. Okay. So, this flow chart kind of thing that I am going to follow. So, Gibbs gave us this ensemble and Gibbs gave us the equivalent probability, ergodic hypothesis. Ergodic hypothesis to an extent was already in Boltzmann, but this was all in this ensemble. That means every system has a constant number of particles n, constant volume V, and all of them have the same energy. So, you can immediately realize that this constant energy constraint is not practical, okay, because your system is in interaction with surrounding media. The kind of A I gave, that if this my number of with water glass, they are in, I cannot keep them in NVE, I can keep them in NVT, but even NVT is difficult. I can keep them in NPT much more easily. That is what a chemist works. Number of particles known, constant pressure and temperature. So, this ensemble is called microcanonical ensemble. This is then graduated to or generalized to canonical ensemble, and then goes to other things that we will not right now, do not need them. So, this is NVE and this is NVT. For the time being, 2 enough, because we now want to try to develop the conceptual of these things, why we need them and how do you work with them. So, when the microcanonical ensemble, remember ensemble is a huge number of mental replica, and the whole idea of ensemble was that I can talk of a probability that was introduced by Maxwell L. Boltzmann. Now, probability of, and I already have my equivalent a priori probability. So, I need to have, now how do I go ahead? How do I now calculate or construct a quantity which can be now given, will lead me to thermodynamics. The first attempt statistical mechanics did to, it was immediately realized, by all these great thinkers, that the first demand on statistical mechanics is to derive thermodynamics, because that is the one that is those days or even now explains all natural phenomena in terms of free energy, entropy, enthalpy, all these things. So, statistical mechanics was geared from the beginning to describe thermodynamics. So, now the idea is, now I have the NVE, I have a huge number of systems, all have constant energy, all have volume V, and all have total number of particles. So, what is different from one system to another system in the ensemble? The difference from one system to another system is in the microscopic state. Each system is in the different microscopic state. That is the most critical realization. Then you immediately realize that what could be a very important quantity, it was realized by Boltzmann, very critical quantity is the total number of microscopic states. Now, what is the total number of microscopic states? How do I calculate total number of microscopic states? And this is a pivotal quantity from which, what I am going to tell to you, from which whole statistical mechanics came out, that the total number of microscopic states. How we calculate it will come a little later. So, if I know that a system, now let us think this, there is a one single, in real world there is only one system. Ensemble is my mental replica. Now, this system, particles in this system are moving, they are randomly moving, they are interacting with each other, they are changing positions, they are rotating, and each of these tiny little movement is taking it from one microscopic state to another microscopic state. Now, it does not take too long to realize that if a system has much more microscopic state, then the system resides in that state longer time. Let me tell you something very important, again I repeat these things. If a system in a given NVT condition has larger number of microscopic states, then the system, they are all same energy. So, the system will spend maximum amount of time there. Now, what is then the measure that state, that particular microscopic state, that macroscopic state which has maximum number, maximum weight or will dominate, so it's almost like theory of evolution in certain sense, so that is where this came from Boltzmann and used by Gibbs, is that this omega has to be a property. It has to be a property. I will give a derivation, but the derivation is again heuristic derivation. It has to be a property which scales with the size of the system in a certain specific way. We all know that thermodynamic properties like entropy, enthalpy are extensive. That means they are proportional to the number of particles in the system. Okay. Now, this thing is enormously large quantity. So, the Boltzmann introduced, and this will become more. This is the Boltzmann formula. I will motivate it little bit more, but let me tell you also, just like the postulates, there is no absolutely convincing derivation of this, and probably there is no need. Many of these things have been verified post facto, but before I motivate further, let me tell you little bit more about how this omega comes about. And as I tell you that this, as I talk, let me repeat that this is, that one formula is the most important formula of the statistical mechanics. Whole statistical mechanics came from that. Okay. So, this is a very simple my picture of getting the giving you an idea of the in a microcanonical ensemble, the number of microscopic states that you have. So, I have this 4 energy levels and 4 energy levels, and total energy is fixed 8. How many way I can distribute that? So, these are the, here you can distribute your system into, so arrows are the systems, I am talking of ensemble, and these are the microscopic, these are all distinct microscopic states, okay. And I have taken care of distinguishability or indistinguishability. So, each of them is one state. Now, what happens if I increase the number of particles in the system? If I increase the number of particles in this number of systems with the energy E fixing 8, then there are many more ways to arrange it. Similarly, if I can increase the number of energy levels, then again many more ways to do it. Okay. Very soon in the real world, when the atoms and molecules are moving, there is a huge number of energy levels. Huge number of energy levels available to the system. A 1 cc of a gas at normal temperature you can calculate, and Macquarie's book has given a of that, we discussed it, as 10 to the power 33 microscopic states. That is a kind of huge number we are talking. Okay. So, that is also the difficulty of doing computer simulation, because there is a huge number of microscopic states one has to sample. So, the microscopic states increase what we call exponentially as the size of the system, by meaning that the energy level. So, two things are coming. Energy levels of the system are determined by the system itself, by the interactions, for example, by Schrodinger equation. So, I am having a self consistency here, because I am taking a system, then calculating its all the energy levels, then I am doing a ensemble construction. Is a very pretty, very beautiful. Then I am doing the ensemble construction. I am saying, okay, I have the energy levels now. Now let me see I have infinite number or billions and billions of my system, which I am going to distribute with the constant that energy is conserved. This is NVE. Okay. I realized very quickly that number of states, that have number of arrangements, my omega is growing exponentially. You can do a simple calculation to show that it can, a simple combinatorics, that it grows exponentially. As soon as that grows exponentially, and I know my thermodynamic properties are dictated and determined by omega. So, in that case, I am now having beginning to have certain insight that I want to describe thermodynamics, and I want to have an extensivity. Then I want to preserve the extensive property, and I want to preserve what is the scaling. So, this is now why it is entropy, and that came from a much complicated and detailed derivation of Boltzmann, that why ln omega was given to at constant energy and volume is entropy. That is the way it turns out that this is the you can regard that this quantity ln omega, omega is more fundamental, and ln omega is the quantity that we call entropy. So, this is essentially a definition of entropy. Do not consider it as though it went like that, entropy came first and then came omega, but for statistical mechanics it is the other way around. Omega is the primary quantity, and that determines entropy. So, it is just exactly the other way around. Now, there is a derivation that is given in many places, and I will just sketch the derivation, though as I told you, this you can regard as well as a postulate, and sometimes when I teach in class I say statistical mechanics should actually be consist of 3 postulates and 1 hypothesis, and one of them, this is the postulate, because in many sense there is no really strict sense derivation of this, but whatever. So, this is the A of omega okay, the derivation is sketched here, and this is the derivation given in every textbook, that you define an entropy function. So, this is the derivation is given in my book, and the standard derivation in every textbook is you define your function, entropy function, in terms of probability. The energy levels that I discussed, that, and my systems 0, 1, 2, 3, I think I remember that I have 2 here, 4 and 2 here, 1, just there are many like that, one of them. Now, so define this function, this is what actually also came from Boltzmann, And I have some interesting tale to tell you that I'll so basic idea was that I define a function which is proportional to the probability it is occupied, it is probability of the system in a jth energy level, because these are systems, arrows are systems, they are systems of my ensemble. Again, my energy levels are obtained by solving Schrodinger equation or even classical mechanics by all the positions and momenta available to the system, which is called the phase space. We described little bit of phase space in the last class, and trajectory. So they are obtained from a given system. Now I construct my mental replica and put my systems, my arrows into different energy levels. Okay. So once I do that, since they are all equally probable, I can find out what is the probability my system is in a given energy level J. Then I construct this quantity. So now, then the derivation says, okay, they are all equally probable. So Pj is, so it is minus Kb, all the sums are the same, probability is the same. So if there are n number of, total number of arrangements, and probability is ln omega, and by p is 1 over ns, because each of the equally probable. So this cancels, and then it becomes pg ln pg. Pg is 1 over omega, pg is 1 over omega, sorry. So this cancels, and then that becomes, the 1 goes to 0 and minus ln 1 over omega minus, so plus kb ln omega. So this is the standard derivation that comes to textbook, that S equal to kb. But even then, even in this derivation, which is heuristic, but it does bring in little bit more physics in the whole thing, that you derive a function. So this is the entropic function. This function defines, entropy is the function that it defines microcanonical ensemble. This is the beginning of thermodynamics, a beginning of statistical mechanics actually, or a relation between statistical mechanics, or a relation of, perhaps the most important relation, where everything flow from this one relation, that S equal to kb ln omega. Yes, because every state is equally probable. Huh? See what the reason I am little bit fumbling is because when statistical mechanics was formulated, Boltzmann and then Gibbs, you have to understand that the theory of probability was almost entirely developed in the mathematics. They were developed in a great extent by 19th century already. So the people, and then they had, both Boltzmann and Gibbs had the understanding that they are going to look at a extensive property, okay, and their new probability is going to scale, probably to 1 over omega, but omega is going to scale as the something to the power n, okay. So that brings the log term. So the whole motivation of introducing log term there, and I am again and again saying this is a definition of entropy function. It remains to be shown this S is indeed thermodynamic entropy, and that was done later. So this was introduced as a function. Boltzmann definition, this was H, it was not S. It was shown by Gibbs that this function is the S, and we are using it as S, okay. And I told you that I will say you something really interesting. The interesting thing is that S is proportional to ln omega, and proportional constant Kb is Boltzmann constant. Nobody yet knows why it is, why Kb is 1.38 into 10 to the power minus, I think 17, no? No, he caught in minus K, but he has, this was his arrow of time. Let not get into that, yeah. So that's why I didn't want you here. Okay, A is equal to Kb ln omega. This is introduced, I would like to tell as the primary postulate of statistical mechanics, but you can say no, this is a function defined by ln omega, and it has to be ln omega because omega is an exponential function of the total number of particles, size of the system. So it must scale as, it must be ln that brings in u a to the power n comes out, and entropy is an extensive property. Okay, and this, as I said, that the people there very quickly realize that thing. But again, I am not trying to justify that. The justification of that S Kb ln omega, S is indeed the describes the fundamental equation of state of thermodynamics and entropy. That is a detailed derivation of that exists in a transition from statistical mechanics to thermodynamics. That thing we will do in the next class, where we will see how S equal to Kb ln omega can indeed describe thermodynamics. That's a still unfinished agenda. That is the thing we need to do next to convince you that S is indeed the entropy. Once that is done, and as I told you, this only equation that you need, no other equation you need. From there you go to Microcanonical Ensemble, you go to Grand Canonical Ensemble, you isothermal isobaric ensemble, everything omega, because you realize immediately that the properties that will come, that macroscopic properties, that particular state of the system which will have maximum omega. Maximum omega means maximum entropy. Stable state free energy is minimum, that also follows from this. So whole of thermodynamics follows from that one equation, in entirety, which is amazing. No, these are all interacting. These are not. What I said is, it is the, when Maxwell did it, the ideal gas, that's, see, whole kinetic theory of gases that you read in your undergraduate is for ideal gas. So in ideal gas means particles pass through each other, but that was not allowed. So he derived PV equal to nRT. Then he derived pressure equal to 1/3 mNc square. They are all ideal gas. But at the same time he allows the exchange of momentum with the ball, which is the billiard ball. So there is a mix of interaction and non-interaction, which is fuzzy, very fuzzy. That's not the way, but that's why Maxwell did and got the right results. Boltzmann, that's what led Boltzmann to remove the inconsistency in Maxwell and try to introduce the interaction. If I ever teach time dependent stat mech, then I always start with Boltzmann kinetic equation. That means the F2, F30, that's where you take a two particle collision and F2, which is two particle joint probability distribution of R1, R2, P1, P2, and by interaction that is changing. But that then you explicitly have the collision, and there is a term that comes in called collisional cross section, which has molecular diameter in it. See, in kinetic theory of gases, you don't need pressure, PV, nRT. PV, nRT doesn't have a molecular diameter. Okay. Then all these you don't have, except when you go to calculate the viscosity, then you need the molecular diameter. Maxwell kinetic theory of gases is many places internally inconsistent. That was Boltzmann tried to do, and he could do only partly. But these are very good issues and very fundamental issues that we bypass in our undergraduate physical chemistry. But I always believe the interface between equilibrium and time dependent statistical mechanics is one of the most fundamental and most intellectually exciting and pleasing to think about these things. Okay, dokie, we stop here now.